Hi, I thought for this video that I would spend my time talking about a problem about the energy that's available in a stream. And I picked this problem because it exemplifies a couple of the big ideas of this unit about the distinction between power and work and energy. And it also applies it to a practical problem. Like, suppose that you lived in a remote place that had trouble getting enough electricity, and you thought, hey, I've heard that there's energy in moving things, and there's a stream that runs through our town, and maybe we can tap some of the energy in that river, in that stream. So the problem is we have a stream that's flowing at a rate of 2 meters per second, and there's a vertical drop in the stream of 1.5 meters. The question is, what's the total power available in the stream? So first, I want to remind what power is. Power is a rate. It's the rate at which energy is being transferred or moved around. Rate of energy transfer. So it's how fast something is happening. And it's usually measured in units in the metric system called watts. But that's a shorthand name for a joule per second. And there's other units that are used in other unit systems that can be converted into that. Work is the process of energy transfer. It's basically what you have to do to get the energy of a system to change. And in so doing, you tend to transfer energy from yourself into the thing or out of the thing that you're doing work on or doing work with. And then, of course, there's energy, which is the stuff that we're trying to move around. And it's kind of circularly defined in our textbook as the potential to do work. And work is the process of energy transfer. And power is the rate at which we're doing that. Okay, so the question is asking what's the power available in the stream. That means we want to know the rate of energy transfer that can be gotten out of the stream, because that'll tell us something about what we can do with it, how much we can use it for, like how many houses it could power. So let's figure some things out about that. So I see there's this speed here, 2 meters per second. And I remember that moving things have kinetic energy. So the stream already, before it falls, has a kinetic energy. Kinetic energy is calculated as 1/2 times the mass times the velocity squared. Now I know the velocity, it's 2 meters per second, but I don't know the mass. It's just water. It's a stream. It has a vertical drop of 1.5 meters. I don't know how much water that is. So I need to do some more measurements of this stream in order to be able to get a sense to survey it and to know what I can do. So let's say you go out and you measure it, and you find that it's about 4 meters wide. I'm just kind of making these numbers up. That seems like a reasonable number for a stream. It's like 12, 13 feet across. And it's only 1 meter deep. So 1 meter deep. And that's the spot, like just above the little waterfall where it drops by 1.5 meters. So that's how much water is coming into that little drop. 1 meter by 4 meter across. So I'm going to imagine that I make a little box that's also 1 meter deep, 1 meter back from that little waterfall. And I want to know how much water is in that box that's 1 meter by 1 meter by 4 meters. So that box has a volume of 1 meter times 1 meter times 4 meters, which is 4 cubic meters. That might not sound like a lot, but it's actually a lot of water that fits in there, because water has a density of 1,000 kilograms for every cubic meter. So 1,000 kilograms per 1 cubic meter times 4 cubic meters, and those units cancel for me. So that's going to tell me that there's 4,000 kilograms of water in that box. So just sitting there in the 1 meter up above the little waterfall, there's 4,000 kilograms of water. So that tells me that that water has a kinetic energy of, kinetic energy is 1/2 times 4,000 kilograms times 2 meters per second squared, which works out to 8,000 joules. And that's before it falls. Already flowing in there is 8,000 joules. So then I want to know how much energy I also get from letting that water fall, and then I'm going to, like, as it falls, as it gets to the bottom when it's going as fastest, I'm going to make it spin a turbine or something like that so I can take energy out of it. So how much is that? So if it drops by 1.5 meters, that means it's going to gain some more kinetic energy, and it comes from the potential energy that it has as it up at the top. And the amount of energy that it gains, this is an energy transfer, is the work that's done to move it up or down that little hill. You calculate work by taking the force that you have to use to move it times the displacement. Well, I know the displacement, it's 1.5 meters. And the force is equal to the mass of the stuff times how strong gravity is, because that's how much I have to oppose in order to lift it or drop it. So I just figured out the mass. It's 4,000 kilograms. And the strength of gravity is 10 meters per second on Earth. That's rounded a little bit, but I think that's a pretty good estimate. And times 1.5 meters. So if I multiply that out, I'm going to get 4,000 times 10 is 40,000. 40,000 times 1.5 is 40,000 times 1.5 is 60,000 joules. That's how much work is done to lift the water up 1.5 meters, and therefore it's how much energy you gain by letting it drop by 1.5 meters. So then I have to think about, well, how much water am I getting every second? Because I was imagining this rectangle that's 1 meter by 4 meter by 1 meter back from the thing. That's how much energy that rectangle has if I drop the whole thing. But how many of those rectangles are dropping every second? Well, because the water is moving at, let me scroll back up here, 2 meters per second, that means, because it's only 1 meter back, that I'm getting 2 of those rectangles every second dropping off that little cliff. So one of those rectangles gets me 60,000 joules. I'm going to get 2 of them every second. And I also get another 8,000 joules for each one of those little rectangles because of how fast it was already moving. So that means I've got 68,000 joules for one of those rectangles, but there are 2 per second, which works out to 68,000 times 2, which is 136,000 joules per second, which I said up above is the same thing as a watt. 136,000 watts, or 136 kilowatts. So that's pretty cool. I found out that this stream, every second, I can get 136 kilowatts. Well, I need to say that better. This stream can provide 136 kilowatts of power, which means 136,000 joules each second. Now my next question, and the one that I'll finish with, is to think about the scale of that, because like that sounds like a big number. But in the US at least, the average rate at which energy is used is 10 kilowatts per person. And if this stream can provide 136 kilowatts, well, then that stream provides power for 13.6 people. I get that by saying 136 kilowatts times one person per 10 kilowatts. Then the kilowatt part cancels out, and you get 13.6 people. So this stream that is 4 meters across, 1 meter high, and has a flow rate of 2 meters per second provides enough power for 13.6 people at best. That's if I'm able to like take all of that moving energy out of it as it drops, which actually is kind of difficult to do. So if this little project to get energy for a little town is supposed to provide for more than 13.6 people, then I need more than one stream, or I need it to be flowing faster, or I need it to be deeper than that, or something like that. So like maybe this stream won't be enough. So those are the kinds of questions that we can answer and understand by thinking through the power, the energy, and the work. So to quickly review that, the power is the rate of energy transfer. We measure that in watts or joules per second. The work is the process that we go through to transfer that energy, and the energy is the stuff itself that we're trying to transfer.